Hi everyone. In this video, we are going to learn how to predict relative acidity. So we're going to compare two acids and figure out which one is stronger and which one is weaker. So remember, in a typical acid-base reaction, we have our acid and then our base, and these are generic forms of each. And typically we have some sort of equilibrium between the reactants and products, so I'm drawing a double arrow. And then we have our conjugate base and conjugate acid. Now also remember that if you have a strong acid, so let's say this acid is strong, that means the conjugate base of that acid will be weak or stable. Okay. Now, there are various things that can stabilize a conjugate base. So down below, you'll see I have a few things listed: charge, atom, resonance, dipole induction, and orbital. So looking at all of the underlined letters, we see that this spells out cardio. Now, in your textbook, they don't include charge really, so they just use REO, but it's the same thing. Here I'm going to include charge and the word dipole because it's a little easier to remember. So if you're trying to determine the relative acidity between two acids, you just have to practice cardio. Now, during this pandemic, I really should be practicing more cardio, but we'll see. Okay, so as we go down this list, the different items become less important. So charge is the most important variable if we're trying to determine the relative stability of a conjugate base or the relative strength of an acid. And then as we go down the list, orbital is the least important aspect, but it does come up sometimes. Okay, now let's actually look at some examples of each of these different items. So we'll compare acids and their strength based on their conjugate bases. So we're going to really compare the conjugate bases of different acids and their relative stabilities. Now, if that doesn't quite make sense yet, don't worry. We're definitely going to go over a lot of different examples. So hopefully that will clear up any confusion. Okay, so let's start comparing acids. So let's start with charge. How can we compare acids based on charge? So let's say we're comparing the hydronium ion to water. So we'll call the hydronium ion acid 1, and we'll call water acid 2. And we're trying to determine which one is stronger. So what we're going to do is compare their conjugate bases. And I'm just abbreviating conjugate there. Okay, so let's see what happens if these two acids react with the same base. So I'm just going to draw this generic base that we have been drawing. It doesn't really matter which base we're using for now. We just kind of want to get a general idea of what the conjugate base would look like. Okay. So what I encourage you to do is to pause the video and figure out what the products are for acid 1's reaction and acid 2's reaction. And then when you unpause, we'll go over it together. Okay. So for acid 1, the hydronium ion, when it reacts with a base, again, it's going to give up a proton or donate a proton. So we'll end up with H2O as one of our products. And then the other product is our conjugate acid. But remember, we're really interested in the conjugate base. Okay, now water, if it acts as an acid, it's going to again donate a proton, so we'll end up with OH minus, which is the hydroxide ion, and our conjugate acid. All right, so again, remember we are comparing water, which is the conjugate base of our first acid, with hydroxide, which is the conjugate base of our second acid. So that's what we're comparing. Okay, so now the question is, which conjugate base is more stable? Okay, so which one do you think is more stable? Or another way to think of this is which conjugate base is less likely to react? So which one is weaker? So in this case, water is more stable. It's less likely to react compared to the hydroxide ion. So you'll notice that the hydroxide ion does have a negative charge, and most molecules would prefer to be neutral or more stable. So water, because it's neutral, is more stable. So what that tells us is that the hydronium ion, or acid 1, is stronger than acid 2. Okay, so H2O is more stable than OH minus. So H3O plus is a stronger acid than H2O. Okay, so if that doesn't quite click, that's okay. Another way to think about this is in terms of equilibrium. So if we think about those arrows up above, I'm actually going to redraw them. So we now know that H3O plus is the stronger acid, and that means that equilibrium favors the products. But then if we look down below at water, or acid 2, its conjugate base has a charge, so it's going to react more easily. So that means that there's probably more of an equal equilibrium here, if that makes sense. And so water isn't going to dissociate as much because its conjugate base wants to keep reacting and reform the reactants. So in fact, the reactants might be a little more favored than the products, which means that water is not a very good acid, compared to hydronium at least. Okay, so H3O plus again is stronger because its conjugate base is more stable compared to our other acid. So when you're comparing two acids, first start by figuring out their conjugate bases, and then compare the conjugate bases. And the first thing you would do is compare their charge. Now, if they have the same charge, the next thing you would go to is atom. So let's talk about atom. So let's compare two acids again. This time we're going to compare H2O and CH4. Now, you might remember from our previous lecture video that CH4 is a really weak acid, but bear with me. We might already know the answer here, but let's just use this as our example. So again, we're going to ask which acid is stronger, and we're going to compare conjugate bases. So we need to show the reaction that each of these molecules would have with a base. All right, so I encourage you to try to determine the products on your own for each of these acids. Okay, so let's figure out the products for these reactions. So for water, we already saw that we would end up with the hydroxide ion and the conjugate acid. And then for methane, we've seen previously that it would give up a proton to form CH3 minus and a conjugate acid. So again, remember we're comparing the conjugate bases. Now, in this case, they both have the same charge. So now we're going to look at the atom involved in each molecule, or rather the central atom. Now, with the hydroxide ion, the main atom there is oxygen. And in the CH3 molecule, the main atom is carbon. So what we're going to do to figure out the stronger acid is compare the electronegativity of those atoms. So this works if the main atoms are in the same row as each other. So if you look on the periodic table, oxygen and carbon are in the same row. So we're going to compare their electronegativities. All right, so which atom is more electronegative, oxygen or carbon? Oxygen. Oxygen loves electrons more so than carbon. So that means oxygen is much happier with a negative charge than carbon. Carbon would prefer to be neutral. So let's write a little note here. OH minus is more stable due to electronegativity. Okay, so that tells us that water is the stronger acid because its conjugate base is more stable. So let me use a different color here. All right. So now what if we have two conjugate bases and their main atom or their central atom are not in the same row? What if they're in the same column? In that case, we would compare atomic size. So, for example, let's compare the acids HCl and HI. So we have hydrochloric acid and hydroiodic acid. So again, we're going to compare their conjugate bases. So let's draw out the reaction for each. Okay, so I would like you to pause the video and write out the products for each reaction. Okay, so in our first reaction, we would end up with the chloride ion and the conjugate acid. And in our second reaction, we would end up with the iodide ion and the conjugate acid. Okay, so both of our conjugate bases, which I'll highlight here, they both have negative charges. So we can't choose the stronger acid based on charge, so we have to go to the type of atom. And chlorine and iodine are both in the same column, so we need to compare them based on atomic size. Okay, so let's think back to our periodic trends. If you go down a column of the periodic table, does atomic size increase or decrease? It increases, right? Because we're adding more and more electrons as we go down a column. Okay, so that means that the iodide ion is larger than the chloride ion. Okay, so if iodide is larger, does that mean that it's more stable or less stable than the chloride ion? So another way to think about this is, do larger atoms accommodate a negative charge better or worse? So larger atoms can take on negative charge more easily. They do have more electron energy levels, so they can accommodate electrons better. So the iodide ion, because it's larger, is more stable. My pen decided to go bold at the end. So again, the iodide ion is larger, it can take on electrons more easily, so it is more stable. Okay, so what that tells us is that HI, or hydroiodic acid, is stronger than hydrochloric acid. Okay, so we've gone through charge and atom. So next is resonance. But before we do that, oh, did I? Nope. Okay, so before we do that, I do encourage you to try the Skill Builder 3.5 exercise on page 106. This focuses specifically on atoms. So it'll give you more practice comparing conjugate bases and their stabilities based on the atom in the conjugate base. Okay, so now let's go to resonance. So let's say that your conjugate bases have the same charge and similar atoms, and you can't figure out which acid is stronger based on those factors. We're going to then move on to resonance. All right, so it's a good thing we already learned about resonance structures. So let's compare two acids again. This time we'll compare ethanol, which has 2 carbons, 1 oxygen, and 6 hydrogens. So remember, this is the bond line structure. So we're not showing certain hydrogens. I'm only showing the hydrogen on the alcohol functional group. And remember that you should be memorizing those functional groups that we talked about in chapter 2. Okay, so now the other acid is somewhat similar. It's called acetic acid. But the only difference is the second carbon has a double bond to oxygen. And you might already know that acetic acid is a compound found in vinegar. But what is this functional group? Can you figure out what functional group is there? And I'll give you a hint, it's not an alcohol. It's a carboxylic acid. So this was in that third row of functional groups that I showed you, and you didn't necessarily have to have this memorized yet, but I just thought I'd ask and see if you knew it. Of course, I can't hear your responses, but that's okay. All right, so again, we're asking which acid is stronger? Oh, I combined 2 words together. I got lazy. Oh, no, I do want the eraser. Oh, it's not letting me erase. It's not happy with me. Let's see if that worked. There we go. Okay. All right, so again, we're comparing conjugate bases. So let's write out our reactions. And I would like you to try to figure out what the products are for these 2 reactions. So feel free to pause the video. And then when you unpause, we'll go over it together. Okay, so ethanol is an acid that we're losing a hydrogen from. So what we would end up with at the end, and actually I'm going to show you a way to kind of draw what's happening in this reaction. It's called arrow pushing. And you might have seen this before, but if you haven't, that's okay. So in arrow pushing, what we do is we show electrons grabbing onto another atom. So in this case, the lone pair of electrons on our base is grabbing onto that hydrogen. And then when that hydrogen leaves, the shared electrons will be left on oxygen. So arrow pushing just means where are electrons going? How are they moving in a reaction? So it's kind of similar to our resonance structures, but this time instead of electrons moving within a molecule, they can move between molecules, if that makes sense. All right, so what this shows us is that we'll end up with an oxygen with 3 lone pairs. And remember, if you see an oxygen with 3 lone pairs, that means its formal charge is -1. And then our other product is the conjugate acid. All right, and then down below, we have acetic acid, and a similar thing is going to happen. The electrons on the base are going to grab onto the hydrogen on our OH group, and the shared electrons will be left on oxygen. So we'll end up with a negatively charged oxygen again. And then our conjugate acid. Okay, so if we look at our conjugate bases, so we'll highlight those. They both have negative charges, so we cannot determine their stability based on charge. They both have the same atom there, oxygen, and carbon, so we can't really compare based on atoms. So we have to compare it based on possible resonance structures. Now remember, if something has resonance structures, that stabilizes the molecule, right? So if one of these conjugate bases has a resonance structure, or multiple resonance structures, it will be more stable. Okay, so let's look at our first conjugate base. So we'll look at the conjugate base of ethanol. So is there any way we can move electrons around? So is there resonance? No, I don't see any resonance patterns. We do have lone pairs next to a sigma bond, but we usually need a pi bond after that, and there isn't one. Okay, so no resonance. What about the second conjugate base? So the conjugate base for acetic acid. Do we have any possible resonance structures? Yes, so we have a negative charge on oxygen next to a single bond next to a pi bond. Okay, so let's draw the resonance structure for practice. Let's see. I don't know if I have enough space. We'll draw it down below. How about that? Okay, so let's show the movement of electrons. So we can move a lone pair from the negatively charged oxygen, and we'll move that down to create a pi bond. But remember, when we do that, we're creating a Texas carbon in the middle. So we have to adjust for that. So we're going to move the pi bond up above to create our other negative oxygen. Okay, so that is our resonance structure, and there's really nothing else we can do there. And I'll just put brackets around the resonance structures. All right, so because the conjugate base of acetic acid does have a resonance structure, that means that it is more stable. All right, so this is our stronger acid, acetic acid. And we'll write a little note. More stable due to resonance. And feel free to redraw those resonance structures side by side. I just ran out of room on my on my page, but normally we would try to show them side by side or above and below each other, just to make it a little neater. Okay, so if you want more practice with resonance and determining acid strength based on resonance of the conjugate bases, I recommend trying Skill Builder 3.1 and 3.6 on pages 95 and 108. So actually, Skill Builder 3.1 shows arrow pushing in acid-base reactions, and then exercise 3.6 goes over resonance. All right, so I think I'm going to stop the video there so it doesn't get too long. In the next video, we'll go over the last two pieces of cardio, which are dipole induction and orbitals. All right, I'll see you in the next video.